Okay, then let's start. Welcome to the second day of the workshop on AI and theory improvers in mathematics. My name is Achim Brucker. I'm one of the co-organizers of the workshop, and I would like to welcome all of you, the people in the stream, as well as our speakers and panel members on behalf of all my colleagues organizing the workshop as well. And we will kick off the second day with a talk by Chelsea Edmonds on formalizing combinatorics in Isabelle HOL. Chelsea was in the UK. She is now moved back to Australia at the University of Western Australia. And yeah, I'm very happy to have her. We are very happy to have her here. And with that, I hand over to her. Chelsea, the floor is yours.
Great, thank you so much, and thank you for the invitation to speak. It's great to still be able to, be involved in this community online. So these kind of workshops are fantastic. Cool. So for those I haven't met before, which I'm sure is quite a few people on the call, I did my PhD in formalized maths, so my background and my expertise from that perspective is formalized mathematics, particularly in Isabelle HOL. I did also have a past life as a software engineer, and I'm now teaching software engineering subjects again. And when I was developing this talk, I'm kind of noticing a few interesting parallels in some of the conversations going on. And so I thought, as part of this talk, I might try to explore some of those. So looking at, well, one, going back to starting with, well, why do we formalize maths, and then what do I mean by this idea of kind of engineering proofs? I want to give a bit of an overview of the Isabelle HOL landscape. So I know Larry probably touched on some of this yesterday in his talk, but maybe I can expand a little bit on that. And then I'll jump into some of the work that I did using this kind of proof engineering approach, particularly for combinatorics in my PhD, which was, only 2 or 3 years ago, but is now quite a different landscape than what we're seeing today, I think, which is quite amazing for the field. And then give some perspectives on how this translates, I guess, into formalized maths today. And as we see more generative AI tools being quite productive in the landscape, and draw some of those parallels that I'm seeing. And I want to emphasize that I am not an AI expert by any means, so these are very much my perspectives, and hopefully some questions or thoughts that might raise some useful discussions later on. Yeah, all right, cool. So firstly, I guess, what do I mean by proof engineering? These two words, I think, have been thrown around to mean quite a few different things over the last kind of decade. Where I was probably first heard was actually in the context of when we started getting really large formalization projects for the first time. So in Isabelle, a classic example of that was Cell 4, which is a formally verified operating system, which was done using Isabelle HOL. And that was one of the first kind of really big projects that suddenly went from being relatively small scale for formalization to something that was mirroring the size of major software projects. And so suddenly a lot of other elements became very important in that. So this idea of we need to plan, design, implement, but then also maintain a formal proof library. And this is now something we're very much seeing in the formalized math space as well. So when I'm talking about proof engineering, I'm talking about that kind of cyclic way of thinking, but also how we go about creating formal proof frameworks and how we might go and look at examining and refactoring proofs to constantly improve them, and also the infrastructure around that. I am going to say I'm particularly focusing on like the proof libraries themselves. So obviously there is a huge amount of engineering that goes into building the proof assistants in their own right. I'm not going to touch on that at all. So I'm very much focused on the proof engineering side of it, hence the title. So I want to then jump back, well, why is this of interest? And I think we need to go back to why do we want to formalize maths? So why do we want to use proof assistants to do this in the first place? And I've been using this particular diagram on slides since 2019, which I think is quite useful now to reflect on the field and how it's changed. And validating complex proofs was always only one part of why we might want to formalize maths. We also had those bottom 2 points of building central libraries, benefiting from advances, which we are very much seeing come into play today, which is quite exciting. And then the last one I think is really important and probably has even expanded a lot more since, which is this idea of, okay, identifying new assumptions, new proof approaches, gaps in proofs, and also just gaining insights from doing maths in a different way. And I think there's a lot of very interesting insights that we can gain from formalizing. So as we kind of are moving forward as a field, I think it's important to keep in mind that formalization has never just been about verifying a proof is correct. It's got a lot of other advantages that it can offer. And this then, I guess, goes back to the slightly more philosophical discussion that started yesterday. And I kind of want to continue. And we think about, well, what's the purpose of a good proof? And this, of course, has been a debate in mathematics for quite a while. There's obviously the purpose of showing a theorem holds, which then in the formal world might translate to verification. But you've also got these really important, and perhaps some people would say more important, purposes of understanding and communicating. And my argument is that I think in addition to having this on paper, this is also still quite important in a formal world for formalized math. So understanding and looking at that formal proof process, but then also the usability and readability of our formal proof libraries to communicate the results and the insights that we can gain from them. So if we now consider kind of proof engineering in that light and kind of keeping that in mind, we've got this end goal of, well, we want modular, reusable, and extensible, and hopefully easy to maintain proof libraries moving forward. And ones that are also easy to use, not just for other people to develop new proofs, but also to understand the existing ones. And I think that this kind of proof of engineering approach has a lot of potential, which I'm hopefully going to discuss a bit more throughout the rest of the talk, around the development of new formal, and even more generally, maybe not even formal, but more mathematical proof techniques and approaches as we continue to grow as a field. So jumping a little bit into Isabelle. So Isabelle itself is a generic framework for a proof assistant. Its most popular instantiation is obviously Isabelle HOL, so higher order logic. And this slide's very much a quick overview of all of its different features. So I think worth highlighting that we do have two IDEs. A lot of people know about JEdit, and we do now have a VS Codium version as well. So a bit of choice. Traditionally, a lot of very good, more traditional automation tools and search tools. The ISAR structured proof language is quite a key feature, which I'll talk about a bit today. And then I'm also going to be talking about Isabelle's module system in a bit. So formalized maths in Isabelle, it's been part of a lot of major milestones earlier on. And as a result, it has really very extensive libraries. It was probably for quite a long time, and even still to some extent, has one of the largest that is available. And this is in the Isabelle HOL distribution. And as well as in what we call the archive of formal proofs. So archive of formal proofs is online, anyone can go and look at it, but there is also an awful amount that's actually in the Isabelle distribution itself. So it's worth always keeping that in mind if you're kind of exploring, hey, has someone in Isabelle done something before, that there are both of those locations where you might find something. There are still definitely things in Isabelle that haven't been formalized in MATLAB, and very much vice versa, particularly with how much MATLAB has grown in the last few years. So kind of interesting to keep in mind. And one of the kind of, I think, quite important difference with the approach to formalized math in Isabelle compared to, say, Lean, is that we don't have one big monolithic library like MATLAB, where everything is interconnected. So the AFP is lightly peer-reviewed, but different representations of the same idea are very much welcome. And this can have advantages and disadvantages, I think, in formalization. So yeah. Also worth noting, for those of you who haven't kind of explored the Isabelle landscape before, each AFP entry can be very large. It could also be quite small. And so in this slide, it's just to give you an idea of the fact that, yeah, there's definitely still a continuous growth of AFP entries. Some of these entries could include hundreds, thousands, tens of thousands of lines of code in them. So it's always kind of interesting to go and explore. And yeah, this was taken at the very start of the year, January 2026. I took the screenshot. So you can see we're still getting more entries today. I think it's worth kind of discussing a little bit around this kind of idea of a proof-assistant choice and why, for me, Isabelle, versus obviously some of the other proof assistants that are out there. And I guess one of the things I want to put across today is that I do believe that using different proof assistants can offer different benefits. Whether that's inspiration for different features, some things being easier or harder depending on what your foundation is, or even just the tooling that you have available. And then, of course, we didn't get the proof assistants we have today without the development of all of the different kind of ideas from different ones. And I think that's quite important as we kind of move forward. So, of course, I think part of the proof assistant choice traditionally was also who you worked with and who you had access to. And that's something that I think has changed to some extent. But from my perspective, I first encountered proof assistants as an undergraduate student at a university that had Isabelle as the kind of main tool that they were using for research. And then my PhD was under Larry's supervision. So obviously, when you have an expert like that available, that was a very obvious choice for my PhD. I still use it today. I'm also exploring other proof assistants, but there are a lot of things I really like about Isabelle. I quite like the flexibility sometimes in the library. I think that's nice to be able to have different representations of different ideas because sometimes it's nicer, but you still want to interlink them a bit. And so that is a potential disadvantage at the same time, right? It goes both ways. Traditionally, Isabelle has very strong automation. When you look at Sledgehammer and Tactics, that's always been one of its kind of things that it's been very much ahead in. It's got this lovely readable proof language called Isa. It's not quite as, I think it's slightly, I guess, shorter maybe, or a bit more concise than lean verbose, but it's definitely more of a readable language. And also because we do have a simpler foundation, the performance tends to be a lot better. And so we have these really kind of large libraries that can be processed pretty quickly, which is definitely, I think, a huge note of everyone who's worked on developing the infrastructure around that. At the same time, it is also an older system. So we do have an older looking IDE as the primary one. Still, the technology behind it's quite modern, but when I open it up in a lecture theatre, you do get students give you a slightly weird look sometimes. Obviously, a smaller development in mathematics community. And I think that community is becoming a huge part of formalized maths as well. So all things to kind of keep in mind if you're just starting out or kind of considering exploring other kind of pathways. Cool. So I'm now going to jump into a little bit about my own PhD work, so several years ago now, pre-Gen AI, and how I went about approaching that. So my PhD was focusing primarily on combinatorics, and it was looking at not just how do we go about formalizing things, but how do we go about formalizing these things in a smart way, the how, effectively, that engineering side of it. So as an example to start off with, let's look at some really basic definitions. So one of the things that I formalized was a field called combinatorial design theory. I then wanted to go and prove a bunch of proofs about hypergraphs. I ideally wanted to be able to still work in that hypergraph language in a formal environment. But obviously, these structures have actually the same underlying structure. And so I guess the questions I started asking was, how can we still benefit from working in that language that is kind of natural to work in, but without having to obviously redo all the results, which would make very little sense. And so this becomes now not just about definitions, but very much about how we kind of put those definitions together. And I guess as an add-in here, I'll just say, aside from the usual formalization challenges, even basic definitions can still introduce some interesting kind of points of consideration. So that might be variations of definitions, but then also the hierarchies that you're building up and different languages, which I just touched on. So while these basic definitions might be something that, yes, absolutely, generative AI tool could come along today and it could formalize a proof on graph theory and insert the graph definition as part of that very simply, because the definition itself for a simple graph is going to be 1 or 2 lines long. I think what's more interesting is then when you look at the hierarchy and the libraries that you're building out of these when you have different variations of designs, hypergraphs, graphs, and suddenly these all become very interconnected, and we need to think about how we do that smartly to enable future reuse and growth and extensibility of this library. And that takes a lot more thought. And it's quite interesting, actually, if you jump into like a Sulip chat today around how we go about defining something, even in the Lean Sulip, it's been quite interesting to watch this discussion constantly happen about how we represent graphs and how we represent them now. So we could extend to multigraphs, or we can extend to hypergraphs, and what that core representation might look like. So even though the definition itself is still very simple, it's still, I guess, resulting in a lot of discussion. Additionally, just for people who maybe don't have background into what I'm talking about when I say hypergraphs and designs, I've got two examples up there on the screen. But a hypergraph is effectively just a generalization of a graph where edges can have any number of vertices, and a design is more set theoretic, basic version of that. So they're ultimately both what is known as an instant set system, where we have some set of vertices in hypergraph language and then some collection of subsets of those vertices. So the approach that I was using to kind of manage some of these kind of definitional challenges, and particularly for growing this hierarchy in Isabelle, was locales, which are Isabelle's module system. So you can think of these like a persistent context there. They've got similarities to structures in Lean, but maybe it probably doesn't all translate. Particularly locales in Isabelle have a very powerful inheritance kind of hierarchy and tool set, which is really useful for this purpose. So I've got an example on the screen of a very basic locale in Isabelle. You can see we're fixing some parameters. We add in an assumption. We can add in some custom notation, either in the definition or within the locale context later on, and that will be persisted now whenever I open up this context and want to prove or define things within it. And locales enable us to establish direct inheritance, but also to indirect inheritance, so maybe after a locale is defined, and then also prove that something is an instantiation of that. So some specific object, for example, has the parameters and meets the assumptions required of a locale definition. So when I talk about this idea of a locale-centric approach, the idea is very much to use locales to model the structures, and purely locales. So traditionally in Isabelle, if you look at the whole algebra library, for example, you'll see a lot of combinations of locales, type classes, records, and different types. And it gets quite fiddly to manage that after a while. And it turns out just using locales, in Isabelle at least, is quite clean and quite a nice approach, and more than sufficient for a lot of these definitions. Effectively combining that with this idea of also using little theories, so only introducing a single concept at a time to a definition, we can really effectively build out a hierarchy that then enables us to avoid duplication and redundant assumptions later on. We similarly want to define things within the structure of that locale, and leverage locale inheritance then to transfer results between structural definitions. So the initial ideas for some of this work came out of a paper by Clemens Ballerin in 2020, and he reformalized a bunch of algebra, an algebra textbook effectively using this approach, and very much demonstrated that this was quite feasible. And then that algebra library using purely locales was what other members of the Alexandria project at Cambridge at the time used to go and formalize schemes. And so these much more complex algebraic structures that we were starting to see, and to really show, hey, yeah, we can absolutely still do that using the foundations within Isabelle. So there's a lot of potential here. And I think another core part of this approach, which I'll demonstrate a little in a bit, is that locales can be used not just to model structures, but they can also be used to model relationships, and to model kind of different proof contexts that you might want to work in quite effectively. So we can use them far beyond just a structural definition. So the naive approach, I guess, to formalizing a particular type of design would be potentially using locales, would be to introduce a locale that maybe builds on a kind of basic locale definition, adds in a bunch of parameters, and adds in a heap of assumptions. So this is a particular type of design that's very well known. It's what my original goal was to kind of build up and formalize when I first started my PhD. And you can see that we're introducing a lot of things all at once here. Which is great until we realize that we've proved a heap of things on balanced designs that require none of the other assumptions of a BIBD. And so suddenly, if we want to go and now do proofs on a design that just has that balance property but not on any of the others, we've got to do a major refactor. So the approach that my libraries took instead was to gradually build up to this definition. And we ended up with a hierarchy that looked a little bit like this. So it's got a lot of different structures even within it. And you can see that each new kind of locale introduces one new parameter, maybe one new assumption to go along with that to make it make sense. And the solid lines here are direct inheritance, so that's something that's established at the time of declaration of the definition. And the dotted lines in the diagram are indirect inheritance. So particularly that was quite useful for constant replication number designs. So you can see here in this previous slide, we had a separate kind of assumption for replication number. But this is something that is actually kind of basically implied by the other assumptions as is. And so what we can do within the locale context is say, yeah, this thing holds, this property holds, so therefore a BIBD should also inherit all of the properties of a constant replication number design. So this kind of hierarchy was gradually built up towards the BIBD, and the ultimate definition was quite simple because it really was just a specialization of a slightly more general version called a T design. So now we have this kind of initial hierarchy of different types of designs that are out there. And we now go, well, what if I want to work with something that's not on this? How easy is it once we start looking at extensibility and extending this work to go beyond that? And it turns out, despite this diagram looking like it's got a lot of lines going everywhere, that it was actually very easy to do. And actually, I think the fact that there are so many lines going everywhere shows how easy it was to work with locales to do all these quite complex different relationships. So I was able to build and prove a bunch of properties on GDDs in a matter of 2 or 3 weeks, if that. And very easily extend this library and basically benefit from all of those basic lemmas that, you know, can take ages to just get established when you're first defining core properties, and just automatically inherit those all straight away. So I'm only proving lemmas as I gradually refine and add a new property or a new restriction to what I'm interested in working on. So yeah, this was able to manage that very quickly, and despite the number of locales in this library growing very, very quickly, there really weren't any noticeable performance issues in Isabelle at all with managing that. So that was also quite a nice bonus of the approach in Isabelle, at least, for this kind of way of reasoning. What I then thought was even more interesting was going back to that kind of initial challenge that I put at the start about, well, what if I want to reason now on hypergraphs, and I want to use hypergraph language? I don't want to talk about replication number. I want to talk about, you know, degree or something like that. And so this kind of overlap that you might have between different concepts. And it turns out locales are actually quite powerful and good at managing that as well. So I could define a hypergraph, which basically just directly inherited from a design or whatever, but basically plugged in different language and different notation in place of blocks. We might start using edges, for example. So I didn't have to completely redo the definition. I just basically had to instantiate it with different notation. And then I could use sublocales to prove that that equivalence ran the other way. So similarly now, anything I prove in about a hypergraph, for example, and using that hypergraph language, I get automatically translated back into the equivalent design part. So you've got these kind of parallel hierarchies that you can build up, and you can now move between these quite easily. And another feature of locales is that we have this kind of rewrites command. And so it means that, say, if I'm working in a design, and I prove that it has a concept that's a definition that's equivalent to a hypergraph context, to a hypergraph concept. When I inherit that and I'm working in the design theory context, Isabelle will automatically rewrite any theorems on that definition to use the design theoretic version of that definition. So you are working quite naturally within the locale context that you want to at that time. And this was also then particularly interesting when we're going, okay, well, what about if we have equivalent structures but different representations of them? And this was something in graphs. So I had a graph theory library. It was fairly basic. It was modeling edges using sets because that obviously linked up quite nicely to the set-based representation I'd been using for hypergraphs. But I was also noticing that in the Lean library, they were using a relation-based definition, and that there were a number of formalizations of graphs using relation-based definitions in Isabelle for reasoning on particular algorithms, for example. So there were clearly times and things where it was much easier to reason using this relation-based definition maybe than the edge-based representation. And so, again, using this kind of mutual inheritance, this was quite possible to do using locales to establish these kind of two basic parallel hierarchies, show that inheritance relationship runs both ways, and then you automatically get that translation for free between the two different representations as you want. This is an example of when I say this was proof engineering, not just the structures, but then also how we can use locales beyond that in a slightly different way than you might have previously. I will say that this is something that when you have this idea of this circular inheritance going on, it's very easy to end up and think it's not possible. Because when you first start doing that in Isabelle, if you do it without quite a lot of care, you can very easily run into this doesn't, the simplify basically goes on forever. It's not going to terminate the proof. So you do need to do that with a bit of care, but it is very possible, which I think a lot of people didn't necessarily realize. So I think just to kind of highlight a few things that I was looking at, I've now had this kind of general library for combinatorial structures and for reasoning on it. And then I went, instead of focusing on proving a particularly famous theorem, which, might have got a bit more attention, but I then went, all right, I'm going to instead focus on actually establishing formal tools for different techniques. And that was, again, reflecting, I guess, my personal interest in the how rather than just what I wanted to formalize. So particularly for combinatorics, like if you read up on it, you've got this kind of bag of tricks that people might use from different disciplines and often apply them in quite kind of ingenious ways to different theorems that aren't always immediately obvious. So you get these techniques that are used in a lot of different contexts. And one of the things that I focused on was the probabilistic method for combinatorics. And this was quite interesting because obviously I was using a bunch of the analysis libraries and measure theory libraries, and also very much was a case where it emphasized the role human intuition kind of plays in formalizing proofs and writing proofs versus how that looks in a formal environment and how we go about doing that. So again, very much I'm focusing on this kind of reusability and modularity of the ideas that I wanted to go about formalizing, rather than just directly going and translating a proof on paper. So to give an example of what I'm talking about here, this is a very basic proof on hypergraphs using the probabilistic method. You can see it's not particularly long. This textbook has a heap of these examples, and they do have a lot of clearly statements and things like that, which of course for anyone who's done any formalization will know that that means there's probably more work involved underneath there for what's going on. So how did I go about doing this? This is a big part of when I'm personally formalizing something, I get a lot of understanding of the mathematics that is going on. I think it is possible to formalize something without developing that mathematics. But then if you want to formalize something where you fully understand it so you can then proof engineer it, so to speak, and make it more efficient and pull out these kind of interesting components, I think you need to fully understand what's going on in the proof. And you could do this on paper, which I think we've had some great discussion of. I personally love just doing it in Isabelle. So often when I was starting a project, I'd do the first thing I'd do would be to have a bit of a hack, just to see, okay, how does this break down? What are the immediate problem points I run into? I'm generally not trying to finish the proof because I know that will take way too much time, but I do want to get a feel for, well, what's involved in this process. And so this is a screenshot I took at the time of doing this for this particular quite simple proof, as you can see. It's worth noting this is in the ISA proof language in Isabelle. So if you are looking at it, I know it's quite small, so I don't mean for anyone to read it, but you could probably tell that one of the reasons Isabelle code can look a bit longer is that if you are using ISA, you are writing the proof goal there, so you can kind of read it quite nicely rather than purely relying on a tactic-based approach. Yeah, there was a number of kind of interesting things that I was noticing when I was first kind of hacking away at this problem, so to speak. And the questions that I wanted to obviously ask was, one, I want to shorten the proof. I obviously want to make this a lot cleaner. Two, there's absolutely some general techniques in here. So we want to make sure those are extracted so that someone who's now going to formalize another similar proof doesn't have to redo them. And three, hopefully set up enough of a framework that if we go and do this again in the future, this kind of similar hacking isn't required necessarily at the start. So basically what my first kind of challenge was is I wanted to translate, well, what does the basic probabilistic method look like on paper? And then how does that look like? What are the steps in a formal environment? And there were a few really interesting points there. One was this idea of introducing randomness to a problem domain. On paper, that would often be something like, hey, color the vertices randomly with two colors, which is great to translate into a formal language. So in a formal system, that means we need to define a probability space. We need to start looking at the measure theory side of things, which on paper you would never do working in this particular field. So that was quite a big difference in just the setup required for the proof, a throwaway line compared to quite a bit of work. And then there was obviously some things that are quite similar. On paper, the proof would often end at 3 because 4 was kind of obvious, but the step 4 was still required a few steps in a formal environment. And similarly for step 3, that calculation, that in turn draws on a lot of different theorems and techniques itself to do that calculation. So there is potential within that particular category in the framework to set up a number of lemmas and theorems for reasoning on those different techniques that can then be applied quite easily to a formal proof. So this was an example of some initial setup that I might do to set up a probability space. For example, in Isabelle, we have defining the measure, obviously getting an instance of that probability space, and then setting up a bunch of useful facts so we can easily feed those to Sledgehammer during the process. Ideally, I don't want to have to redo that within every single proof. One of the things that I set up was a way to effectively use locales, again, more this time as a proof context, and have a number of different kind of representations of different probability facts, combining a probability space locale with a vertex, with a hypergraph locale, for example, to reason on different ways you might introduce randomness or different properties you might want to reason about randomly over the vertex set, for example. And this meant that you did do a lot of that setup work within one of like kind of the top locales in this hierarchy, but then you basically just did a bunch of rewriting. So for example, for the vertex color space, I was really just saying, hey, I want this to be something where I'm reasoning over the set of possible colorings, you know, and it made it a lot simpler later on. So I was able to actually apply the same kind of framework, and I go into a lot more detail. I'll include a link to the paper at the end of the slides if anyone interested. But I was able to apply the same framework to go and reason on graphs because I'd proven that equivalence between the hypergraph and the graph representation. And then I could say, okay, because a graph is a hypergraph, really, just specialization of it, I basically got all of this kind of work on setting up probability spaces for free to then go and reason on, instead of vertex colorings, I think selecting a subset of vertices randomly in a different context. So this means now in our actual proofs and any proofs that I'm doing on this, it's this nice little one line. So a bit more like what you would see on paper. And we get a bunch of things basically almost kind of for free. I mean, it took a bit of work to set up, but it's obviously going to be easier from this point onwards. And that means that now when we look back at this kind of proof, what does it look like? I've got the proof on paper on the left-hand side, the Isabelle proof on the right-hand side on the screen. And what's quite nice is we get this fairly nice translation, I think, between the two. So you can kind of see how each step in that basic method might then translate across into Isabelle instead. And realistically, this is a pretty nice ratio, I think, when you think about the average proof on paper versus proof in Isabelle. Now, obviously, we know that there was a bit of work and framework set up, but now for future proofs, they can all benefit from that. So we can get this kind of similar pattern and not have to redo all that base kind of work over and over again. So this particular bit of work, I then went on to extend. I formalized a few different probabilistic kind of techniques for doing those more complex calculations and looked at a few more different, more advanced variations on proving this kind of property. And so it was very nice to be able to reuse those techniques and proof contexts in every case. I also want to highlight, because I've been talking about the fact that, well, from doing this kind of proof engineering, you can get some interesting insights. So what were some of the ones from this particular bit of work? I think for me, the intuition, like how that human intuition translated into from on paper version into the formal environment was really quite interesting. One of the things I noticed, obviously, besides the probability spaces versus color randomly, which one of the big differences, but one of the other things that was quite interesting to notice was some of the physical intuition that was often used when reasoning on independent events when you're thinking about probability. So I actually went back to my high school mathematical textbooks and some of my undergrad textbooks on this. And sometimes it's interesting how these more introductory texts, when they introduce the idea of independent events, they very much appeal to our physical intuition as to what does it mean for things to be independent of each other when we're talking about probability. And then beyond those introductory texts, even in research papers, etc., quite often I would see this kind of throwaway line of, well, these things are independent, so we can do this calculation via the multiplication law. But of course, in Isabelle and in a formal environment, the formal definition of independence is that they meet the multiplication law. So you've got this kind of cyclic bit of reasoning. And so some of the proofs, which because it's kind of appealing almost to this physical intuition, it doesn't translate quite as nicely in the formal environment. And so that was quite an interesting kind of thing to reflect on when we think about how we think about maths on paper and generally versus when we're looking at the formal definitions of certain properties. And then there were also, I think, some interesting kind of insights into the actual libraries. And this was an interesting case for Isabelle's definitions. I'm not going to go fully into that now, just because of time, but I think that's also taking the time, obviously, to go through these proofs carefully. You realize where I think the definition of Isabelle is completely fine still. It just had a slight limitation with how it was defined. And so you get that kind of constant input as well, which obviously in future variations you can feed back and look at how we could change and improve upon that to keep using it. So if I kind of reflect on that work particularly, which as I said is now like 2 years old, a lot of the main results of that work is really not about all the nitpicky kind of formal proof details, but the structure and the strategy and the approach taken and the insights that kind of led to. A lot of the time that I spent wasn't just on formalizing it, but it was on really thinking about the problem and how to best kind of approach that, which in my mind is much more of the proof engineering work rather than the other way around. So I think potentially to a greater extent, I probably spent sometimes too much time refactoring certain things. So I'd have something formalized and then several weeks later I'd still be working on it. And then I needed to finish my PhD, so I needed to hurry up and stop doing that. But you get this kind of back and forth that I think is quite important and quite useful to get some nice results. From my personal perspective, I do think that the manual time I put into formalizing proof was necessary to gain some of those insights. And again, personally, how I approach doing formal maths certainly helped me gain a lot more understanding of those proofs. So I am, again, a software engineer by training. I did an undergrad degree in maths as well, but I haven't done kind of graduate level research other than formalized maths in mathematics. So for me, I actually spent quite a lot of time just understanding different mathematical concepts, and formalization really helps me with that if I do it manually at the moment. So I guess I'll kind of now go into some perspectives as we kind of look. So I did this work 2 years ago. I've worked more on verification of software ideas and programming language concepts since, and now I'm kind of diving back a little bit into formalized maths again, and have been reflecting a bit on how things have changed. So I thought I'd start off by touching and going back to this kind of software engineering discussion, because obviously generative AI is having a huge impact on software engineering. And as someone who is teaching a second-year programming course, this is something I'm very much kind of keeping in mind. And I've had the chance to talk and meet with a number of kind of industry advisors recently on how this is changing in the industry for software engineering. And there were a few observations there that really stood out to me. For many people, the bottleneck used to be the implementation, but that's very much not the bottleneck anymore, the process. It's very much now more on testing, peer review, and deployment of the project. And obviously, of course, design is also becoming increasingly important. So that initial kind of thought process. One of the things that I'm hearing from a lot of these people talking to them is that the tools amplify the ability of the engineer, which can go either way, right? So if you've got a really good engineer who really understands all the foundations, you can significantly amplify both the productivity and the kind of the code that they're producing. But that doesn't necessarily work for everyone, right? Because we still have to build some of these foundational tools. And so broader engineering skills are becoming much more important for software engineering in the workplace. But as is also deeper kind of technical knowledge. So that's not just how to program, but understanding why things work and domain-specific knowledge and the ability to critically analyze things. So these kind of more general skills are becoming much, much more important. So how does this kind of translate, and what are the parallels and what are the differences, again, from my perspective, in formal proof and particularly formalized mathematics? So I think for us, design has always been very important. And this is why across projects, and Kevin touched on this a bit yesterday, we are going to be spending a lot of time thinking about how we go about defining things. And so that's always kind of been a big part of, I think, any aspect of formalization. There is potential that we're going to see a similar, obvious decrease in the implementation of those proof details. I think that's quite likely. We're kind of seeing that. The difficult part might be the definitions, but proving individual theorems might be able to be sped up quite a bit. So as a personal kind of a standpoint, I can't tell you how many hours I spent during my PhD proving really simple summation proofs that were just being very finicky to work. And that absolutely is not an Isabelle problem. I've talked to people who are also working in Lean and Rock, and that's something that I think we all were facing when doing these kind of proofs. So I'm quite excited by the thought that I could potentially not have to do that. And that's something that we could outsource Gen AI tools. As a slight downside, obviously doing formal proofs can be a lot of fun. So doing them manually is something that I personally actually quite enjoy for the most part. And again, those observations from earlier that these insights can come from the implementation, which I think is more so the case with formalization than it is with programming in particular. So is it more important? Should we be asking ourselves to keep a human in the loop so we still get that benefit? There's absolutely a parallel from testing and peer review perspective, right? We're seeing a lot more time required, and unlike software, we need both proof assistant and mathematical experts to be doing this. So it's less testing, but more peer review to check that the formalization actually does formalize the result that we're interested in. And I think more than that, avoid suddenly bloating proof libraries. So I think formal maths is really important that we both have a performance aspect, but also that understanding aspect, and this kind of ideal to go towards a good proof and a good quality proof. That's quite important. And in many ways, I think that's reflected in some of those kind of more general proof engineering skills, all of these different ideas. I think there's also quite a few differences that are worth noting. So in my perspective, I can see more alignment between using proof assistance purely for verification with what we're seeing with the software engineering kind of changes as well, than maybe if we want to benefit from all those other aspects of formalizing something. So as an example, if you were just trying to prove a program was correct, you might go, I have a precondition, I have a postcondition. Does it verify the theorem? Excellent, move on. That's all. Does it verify it does what I want to do? We can move on. That's all I wanted out of it. You don't necessarily care about how it goes and does that. And that would be similar to potentially in a software engineering landscape, like allowing a slightly lazy implementation through because it still does the job correctly, it's still relatively efficient, and it would take you more time to refactor it yourself than to do it again. That's something I'm getting from talking to engineers. So it's quite interesting in that perspective. But there's a very different target goal in that perspective for a software product. There's a lot less concern with the precise details of the how than the end goal, which is a product that works and meets requirements and probably also makes a bit of money along the way, right? So especially in that kind of for-profit environment, very different kind of landscape and end goals than what we might be working with. I think the formalization community traditionally has always cared about the how. And this is very much reflected in papers that you'll see at conferences like ITP and CPP, and how we go about doing things. And I think it's then is perhaps even more so for formalized maths. If we go back to this philosophy of what a good proof is and why do we have a proof, right? I again would argue that that's important not just on paper, but also in the formal environment. Mathematics has always been really interesting in that we've always cared about different approaches to a problem that has been solved before. If someone comes up with a cool new shorter proof to a theorem, that's still really interesting to investigate because of some of the things that might have been discovered during that process. And in that way, we could potentially look at formalized maths as just another way of, doing proofs again, and how we might get the new insights from that. I similarly think, and I'll put this and I'll discuss it, Gen AI is also quite likely to amplify the ability of the proof engineer in a similar way. So before I kind of went into this talk, I obviously wanted to do a few experiments myself. I will say that the caveat that these were mostly with kind of free tools / tools that I could get pretty cheap, or through like trial kind of things. So I'm aware that this is kind of augmented by me also reading a lot of what people have been capable to do when they have access to the paid tools and you're putting a lot of money into it. But what I've personally found in my experience is that developing definitions, simple definitions absolutely can do, but again, it took a lot of prompting to get it to go down to the modular variant. So at that point, I may as well have given it the exact spec of what I want, how I wanted to break down, and at that point, I may as well have formalized it myself. So I didn't really see a lot of potential for that. And even when giving quite precise instructions, it tended to try to take shortcuts, which is quite interesting. I see a lot of potential for refactoring definitions. I think this came up in discussion yesterday, and I think it's still very much the case from some of the initial experiments I've tried. I'm also playing around with a few different proof assistants at the moment. So one of the things I tried was, just out of interest, what happens when I try to translate some stuff from Isabelle to Lean automatically. I think it was relatively useful for a first pass. There were some minor things that was obviously going back and forth and cycling through things for a bit. Some proofs had sorries. I did note a lot of proofs were quite long, and at first I wasn't sure if that was just because of differences in Lean and Isabelle, but looking at the Lean library, it was very much just using basic tactics unless I prompted it to use one that I knew was slightly more powerful to discharge a certain goal. So you do have those kind of things. I also suspect it wasn't particularly idiomatic, so to speak. Obviously, Isabelle and Lean do have different foundations, so your definitions are going to look somewhat different. There's absolutely things in common, but there are still differences. And so that's something, if we are using it for this purpose, that we might want to keep in mind. I had very limited success for simplifying proofs, unless I started giving it very specific ideas. I had a lot of hallucinations and really bad attempts when I was trying to get it to do that. Just a few interesting observations. And again, with the caveat that I'm aware there are some of the best models available when you have the money to put into them. But kind of from that, a few opportunities and things to maybe be aware of to finish up. So obviously, I think this is an exciting time for this. This is for our community, right? There's a rapidly growing interest in formalization when we're looking at AI and mathematics, because it does offer at least a partial solution to some of the hallucination challenges. You still get several instances where it's going to go and chuck an assumption or something in there that it shouldn't have. So there's still a lot of careful checking that needs to happen, but maybe less so than just a really convincing pen and paper proof that actually has some major flaws. I see a potential definitely for easier translation of proofs across proof assistants, which potentially excites me personally, because I think it would be great if we could get to a point where you can use a proof assistant depending on what you think is best for the task, to kind of develop ideas initially even, and benefit from different features that different tools offer. Obviously, it substantially lowers the accessibility boundaries of such formal tools, which I think is really exciting just to get more people involved in the community, and significantly reduce the amount of time on mundane formalization tasks, because they do absolutely exist. Maybe less so than software engineering, but there are absolutely some things that you're formalizing that just take an annoying amount of time sometimes, where you're not going to get particularly interesting insights from them. I think there's a lot of opportunities to leverage existing and more traditional automation tools and other proof assisting tooling. So I know there's something people are looking into, and even were initially, like when LLMs were kind of first coming onto the kind of scene, I know it's something that people were looking at in Isabelle, this kind of overlap between Sledgehammer and LLM related tooling. And I think that's even more so the case now, just because we've got these tools that can generate a proof that works. If we can leverage these more traditional skills, that I guess reducing that reliance or expense as well could be quite useful. And I guess then a challenge that I want to put out there is obviously if you've got a bunch of work, I know mine isn't the only work that's gone and put effort into thinking about how we might structure a proof, the framework for the proof itself. So is there a way that we can start looking at training these models to very much recognize those good proof engineering patterns and frameworks and suggesting those. And that might already be being done to some extent. But I think that's a really potentially interesting pathway to explore. I think there's also a few possible drawbacks. And I say possible because I think for the most case, they're very much manageable. And it's more going to depend on how we as a community react to them. And again, this also possibly is slightly coming in with my perspective as someone who's quite at the early career stage of an academic career. So traditionally, if you look at a lot of formalization papers, the contributions will be the first formalization of this. And I think potentially we need to think about if that's actually the most important part anymore. And already we are absolutely still getting papers that aren't the first formalization, but have come up with a new way of doing something. And I think that if we can keep ensuring that those kind of papers are getting through and being recognized, I think that's quite important. And I'm not just saying papers, but also work and general work in the libraries, etc. So it's not just about, oh, we formalized this thing, but it's also thinking about the how. And that really plays into kind of mitigating any potential deterioration of the quality of formal proof libraries, which we obviously want to avoid, and in turn leads to peer review challenges. And I know MathLib is bearing quite a brunt of this at the moment. We maybe haven't got quite as much of this as an issue yet in other proof assistants, but absolutely the volume of things that might be starting to come up and managing things that aren't necessarily great quality. And managing that kind of position is quite a big challenge that we have to really think about. Again, just highlighting that I think we want to make sure we're not losing some of those other insights. And this, again, this last point comes more from my current position, as an earlier career researcher. I don't have access to funds. I don't have a major grant myself yet, at least. And so I am quite aware that formalization has previously always been free and open source and something that anyone can do if you have a computer that can basically cope with a proof assistant, which usually isn't too high a kind of boundary to do. And it is worth, I think, us noting is that the most effective Gen AI models aren't free or open source. And that is a challenge, I think, that we need to kind of keep in mind, and more of an ethical challenge as we kind of move forward. And so I do really appreciate personally when I see kind of people releasing different kind of ideas, and I'm quite excited for what people can do more in the open source space in this regard as well. I also want to add in a quick challenge on education. So I love teaching personally. I'm seeing a lot of challenges with teaching foundations in software engineering, and I can see the potential for this to creep over into the formalization world as well. So as I kind of indicated, peer review of formalization is becoming much, much more important. And having the experts, both mathematically and in the proof assistant of choice, to help with that is really important. And personally, I know that a lot of my expertise in Isabelle has been built up by doing a lot of proofs myself and realizing what does and doesn't work. And I'm still absolutely still building kind of that expertise at the moment. But it does mean now that I can look at something and pretty quickly go, well, that's rubbish if I'm seeing it. Or, you know, that's a really bad way of doing that, and fix it. And I'm doubtful that, you know, someone who maybe just jumped straight into it would be able to do. So I would really encourage, and I think the importance of also teaching how to use proof assistance really well is going to become more important as well to help mitigate this. I would note that I think Isabelle is our proof language kind of helps quite a lot here. You still have readable proofs which can be followed relatively well without opening an Isabelle editor, and so that's a nice little bonus. But yeah, I do think education of using proof assistance is going to become quite an important topic in its own right. And so it was great to see that featured in yesterday's workshop. There's a bunch of generative AI tools being developed in Isabelle. This was just me going through the Isabelle mailing list and seal it from recent things, pulling out a few kind of different things that I've been seeing. I've worked with Andre before, and so I'm quite excited to see. I know we have a shared regard for good proofs and proof engineering, so I'm quite excited to see what might come out of that second project over the next few years. The others were just ones I haven't looked into myself. But yeah, research is very active in the Isabelle space. We might not have any of the big companies, but it is great to see some of that work looking at different ITPs as well. So yeah, just to kind of finish off, I think it's a really exciting time to be a researcher in this community. I think these tools are definitely here to stay, and there is a question, I guess, and a challenge I'm going to throw out to everyone on the call and to the community about how we leverage them to our advantage while navigating those possible kind of drawbacks. I personally think some of those observations, if we look at the software engineering and formalised, are quite interesting, and it could be interesting to see how that continues to develop. And I guess to throw it out there as well for anyone who maybe is just starting out, and obviously Lean is a great starting point given the community and the libraries that are available there at the moment, to, you know, kind of say, hey, also explore some of the different ITPs. One of the things I'm doing quite a bit at the moment is formalizing things in different kind of assistants and comparing what that looks like. And I think that's quite interesting to do. So I think we can continue to learn a lot from those different communities that have developed over time. But yeah, I think that's everything that I had, and I'm probably out of time. So I'm happy to take a few questions. I've got my contact details there, and I'll be around for the panel and on the seal for the rest of the day as well. So thank you very much again.
Thank you very much.